All right, so welcome to Math 344. This is lecture, I believe, 15. And what I want to do today is I want to finish the backgammon doubling problem, and then we'll move on to something else after spring break. Given the number of people who will not be here on Friday, we'll just reschedule that class to some other time. All right. What I'm really interested in doing is going through my logic, and then if you can tell me what I'm doing wrong, would love to hear. Or if I'm doing something right, let me know. I'm getting a slightly different answer than a lot of people. And so what I want to do is I want to go through how do we analyze something like the doubling problem. What makes it so challenging is that we can keep doubling back and forth, and we need to keep track of who has the doubling cube. That's going to be extremely important. So one part of the homework was to analyze if you start off at K, what's the probability you hit N before you hit 0, where we flip a fair coin each time. So I want to quickly go over how you would solve that. Then I want to go over a simpler basketball problem, and then hopefully solve the doubling problem. Okay, so let's get to it. All right, and so the first thing is the random walk problem. The mouse is not trying to move the mouse. Click continue. There we go. Okay. So what I want to do is the random walk problem. So start at K, always move to K, let's just say move up 1 with probability 1/2, down 1 with probability 1/2. What is the probability we hit N before 0? So, beautiful diagram. Here's 0, here's N, 1, 2, ... N minus 1, N minus 2. And then somewhere over here is K, K plus 1, and K minus 1. There are a couple of probabilities we immediately know. We know the probability that we hit 0 before, before we hit N. If we start at 0, we know the probability we hit N before we hit 0 if we start at N. So all probabilities are for hitting N before 0. And so at the extreme points, it's 0% and 100%. Imagine we know that this is, PK minus 1, PK, PK plus 1. Now, really, I should put another subscript because it depends on N. So really, we'll have this as a function of N. You give me an N and you tell me my location, there's going to be a probability. And we have a really nice lemma. And the lemma is that PK of N is 1/2 PK plus 1 of N plus 1/2 PK minus 1 of N, which is PK plus 1 of N plus PK minus 1 of N over 2. It's the average value. And the proof is pretty straightforward. And we'll make a little flow chart. So proof. So say we start at K. Then with probability 1/2, we're at K plus 1. And then with probability 1/2, we're at K minus, well, maybe I should call this K minus 1 because that's going to the left. So that's K minus 1, that's K plus 1. And by definition, the probability we win here is just PK minus 1 of N. Similarly, it's PK plus 1 of N over here. So we get PK of N is just going to be the probability of each branch, 1/2, which is going to then be PK minus 1 over N plus 1/2 PK plus 1 of N. So if we know the probability of two neighbors, we immediately can deduce the probability of the number between them. So in particular, as a nice corollary, can do n equals 2 to the m easily. And the reason is, we start off when, m equals 1, so we would have 0, 1, 2. This is clearly 100%, 0%. By symmetry, we could argue that the middle is 50%, or we just use our lemma and we get that this is 50%. When m equals 2, now we have 0, 1, 2, 3, 4. This will be 0%, 100%. And then if we start off at 2, if we want to know what's the probability we get to 0 before we get to 4, what would we do? We could argue by symmetry for that, right? And so now that we know that that's by symmetry, that would be, say, 50% by symmetry. Or you could try to say reduce this to the previous, but now we're doing steps of 2 rather than steps of 1. Is that we look at a whole process and say, I'm going to do this whole process, and I only care about when I've eventually moved to 2 steps. And I have a couple of things that could happen. I could take 2 steps to the right. I could take 2 steps to the left. I could take a step right, and then a step left, and then a step right. Well, if I do those last 2 cases, there's no net motion. So I might as well just look at moving in steps of size 2. And each one is going to happen half the time. And so if I started 2, I have a 50-50 chance of getting to 0 or 4. Similarly, if I went from 0 to 8, I could argue I might as well consider myself moving in steps of size 8. So could also argue by moving in net steps of 2. Because we're never going to care about n. And now we can use our lemma and get that this would be 75% and 25%. And then just lather, rinse, repeat. Every time we do this, we're going to double. We'll take the results we already know and fill it in. So is everybody comfortable with doing things for 2 to the m? Okay. So now the question is, what if n does not equal 2 to the m? Well, let's try to think of what we could do in the case like that. So imagine we have 0, 1, 2, ... k ... n, and assume we know the configuration here. So let's assume no for n, try to find for n plus 1. So we want to extend this one more. Okay. What's the probability we win if we start at n plus 1? So what's the probability we would hit n plus 1 first before we hit 0 if we start at n plus 1? This is just 1, right? If we're starting at n plus 1, what's the chance we hit n plus 1 first? 100%. Similarly, if we start at 0, what's the probability we hit n plus 1 before we hit 0? 0%. All right, now we want to figure out everything else. Okay. So what if we are at n? Let's try to handle that case. What's the probability if we're at n that we go to n plus 1 before we go to 0? So start at n. What is the probability that we hit n plus 1 first? So go to n plus 1 from n before we hit 0. And again, my subscript was where I start, and the argument is how many points I have. So can somebody tell me one way I might hit n plus 1 before I hit 0? So what's one way, if I'm starting at n, that I could hit n plus 1 before I hit 0?
First one goes in your direction.
First one goes in my direction, right? So let's let this equal x, just so it's easier to write. So x would equal 1/2. That's the probability that I would get here. So if I draw my tree, I start at n. Half the time I'm end at n plus 1, and that's what I want. The other half of the time, I am now at n. Sorry, n minus 1, right? Now, of course, what could happen at n minus 1? So I'm at n minus 1. What could happen next? I could go to n minus 2, or what else could happen? Back to n. Is there any way I can get to n plus 1 without going through n? So what's the probability if I'm at n minus 1, I hit n before I hit 0? So what's the probability I hit n before I hit 0? Yes.
It's just n minus 1 over n.
It's just n minus 1 over n. So we know with probability n minus 1 over n, we hit n before 0. And now have probability x. Because once we're back at n, we've just reset the game. So 1/2 of the time, we're going to end at n plus 1 on the first toss, plus 1/2 of the time we go to n minus 1. Once we're there, it's n minus 1 over n that we get back to n. And then the chance that we win is just x. All right, so we just have to solve this equation. So this is the same. I'll multiply this by 2 over 2. Well, actually, let's do 2n over 2n. So if I subtract, I would get 2n minus n. So I think it's n plus 1 over 2nx equals 1/2. So x equals n over n plus 1, which is exactly what we wanted. So if we know the answer from 0 to n, if we know all those values, we now know going up to n plus 1 if we start at n. Yes. I think you're going to make the comment. Or...
Well, I actually did the proof this morning, and the one assumption I made was that you know that this is true. Like if you start at n, then it's n over n plus 1.
Right.
So that, like, you just do the rest. So,
right. So once we have this, now what we can do in general is, here is the picture. Here's 0, 1, 2, ... k ... n minus 1, n, and here's n plus 1. And we know this is 100%, this is 0%, this is n over n plus 1. If we're at k, what's the probability we hit n before we hit 0? So if at k, the probability we hit n before 0 is what? Is k over n, because we're assuming we know the answer is k over n. So if we call this, so we get p k of n plus 1, would be first I have to get to n before I get to 0. The probability of that is going to be k over n, right? And now once I'm at k over n, once I'm at n, what's the probability I get to n plus 1 before I get to 0? So this is to get to n. And then it's just going to be, what do I multiply by? What's the probability I get to n plus 1 before I get to 0 if I'm at n?
N over n.
Right, that's what we just showed. So we now use what we just showed. It's just n over n plus 1. And this is the probability get to n plus 1 before get to 0 if start at n. Just proved. And lo and behold, k over n times n over n plus 1 is just going to be k over n plus 1. So once we know one value of n, we can just keep walking up. So it's actually enough to do just the case of 0 and 1, where we know it's 0% and 100%. That's all we need to do. We can just keep adding 1 point and walking like that. We don't actually need to do it by powers of 2 and filling in and trying to play games. That doesn't mean you can't do it. You know, I love the fact that there are multiple ways of seeing solutions to problems. But for this, I think the easiest way to do it is if I know it for some size, all I have to do is show that I can do it for the next size. And the idea is there's no way I'm going to get to n plus 1 without going through n. Okay, so we're comfortable on the random walk problem. Okay, so now let's go to the basketball problem. Who are my favorite basketball players from my youth? Bird versus Magic, right? I'm old. And actually, I really should put Magic in what color? Yeah, I was gonna say, is it yellow or purple? I would have done purple. Then let's do purple. We're also at Williams, and so whenever we have an opportunity to put purple into a problem, I think we should take it. I'm not going to keep doing this because it's time intense. But you know, the goal was the problem. First basket wins. Bird always hits with probability P. Magic with Q. And I could do P sub B for probability bird. I could do P sub M for probability magic. I'll just use different letters P and Q. You know, bird shoots first because I'm biased. And we want to know what's the probability bird wins. So let X, which is really a function of P and Q, be the probability bird wins shooting first. Okay. Do you think that's the same as the probability bird wins if Magic shoots first? Only if Magic can't make a basket, right? And that is not a reasonable assumption if you know anything about basketball. So it's going to matter, and we need to keep track of who is shooting. Gee, this sounds a lot like the backgammon doubling problem, where we have to keep track of who's shooting. X is the probability bird wins. What if Y equals the probability bird wins shooting second? Can you think of any relationship between them? Is there a simple relationship or is it a complicated relationship? Think of extreme cases. What would be an extreme case for Magic?
He always makes it.
He always makes it. So if Magic always makes it, then Bird's probability of winning on the second shot is 0. Now, does that impact what maybe XPQ is? Because if Magic always makes it, Bird's got to make it on his first shot or not. So XPQ would just be P in that case. So, you know, one question is there a simple relationship between X and Y? So, you know, I'll let you think about that. Yes.
Is it Y equals 1 minus 10 x.
So the conjecture is y is equal to 1 minus q times x. Yes, and that is correct. And so what happens is that would mean Magic would have to miss his first shot. And then from this point onward, it's just like Bird is playing. And it's just like Bird has started the game at first. So we do have a relationship. We don't have x plus y equals 1. We have x plus y equals q. Qx. So x plus y equals negative qx. Oh, no, sorry. No, I don't want to write that because it would be x minus y. Y minus x. Okay. Okay, so let's solve this. We've already solved this, but let's solve it using a flow chart again. So here's the start, and Bird has the ball. And so x is the probability he wins. So half the time, Bird makes and wins. Oh, no, not half the time, sorry. What's the probability? It's not 1/2, it is. What's the probability Bird makes? P. And what's the probability Bird misses? So 1 minus P, Bird misses, Magic shoots. Okay, now that we're in this situation, Magic is shooting. And now we have two possibilities. And with probability Q and 1 minus Q, so Magic makes, Bird loses. And now Magic misses, so it's like we restart the game. And from this point onward, the probability that Bird wins is just going to be X. Because it's like we've restarted the whole game. So we get the equation X is equal to P plus 1 minus P, 1 minus Q times X. So we get X is equal to P over 1 minus P, 1 minus Q. Okay. Any questions about the basketball game? So good. I find the flow chart a really helpful way for me to keep track of what's going on and keeping track of who is shooting, because that makes a huge difference in this game. Okay, now it's time to look at the backgammon problem. I wanted to just do this to get us all on the same page because we're getting different answers. And again, it is quite possible that I'm the one who's making the mistake. This is going to be recorded, posted on the internet, although there may be a technical malfunction and something might happen to the video. If I look really foolish, one never knows. So try to see if you can find where I'm making a mistake. Now, one of the things we're assuming in this problem is that we have a reasonable model for the backgammon game to try to figure out when to double. That it's the first one to 100 points or 1,000 points, some fixed number of points. So to some extent, this problem is inspired by backgammon, but we can now just say, we want to study this problem. This is a simpler version of backgammon, where first one to 100 wins, and you'll keep tossing a coin, and you decide when you want to double. And if you double, you decide when do you want to accept. And we'll figure out what is the optimal strategy in this simple game. Then the hope is that this models a backgammon game. It could be the situation this becomes actually a bad model because if you have to get to 100 points, what's the greatest swing you can have in probability after a toss? So first one to 100 wins, we toss a coin. If it's heads, you move up a point. If it's tails, you move down a point. 1/100. So you can't have a huge swing. You can easily imagine, towards the end game in backgammon, where you just roll double sixes, and now all of a sudden you go from a position where the only chance I have is to roll double sixes, and now all of a sudden I've got the lead, and I'm going to automatically win on my next turn. So you could have a situation like that where you have huge swings of probability. So the assumption that there's always going to be a very small movement in probabilities is unreasonable. Yes.
Is there a way to like simulate that? So like there's a 90% chance that you go up.
Right.
For
So
100 for like a 10% chance to go up like a 50.
So we would have to make the model more complicated. This simple model cannot describe backgammon at all moments in time because it only allows for small changes in the probability. But we could say that at some point you go from needing 100 points to you now need just 10 points. And we rescale how many points you have and we adjust. So it's important to recognize the difference between your model and reality. So I am not claiming that this is a perfect model for backgammon. I'm just saying, if we choose this as our model, what are the consequences? Do these consequences seem reasonable? The biggest caveat is our model assumes continuity almost. If first to 100 wins only change probabilities by 1/100, not big. So this could be a bad assumption towards the end of the game. All right. So what we're going to do, and I hope, if somebody's still looking for a paper to present, the Great American Shootout, if nobody's claimed that, is a great one. Whoever makes the basket from the furthest wins. We're going to represent the game state just by the probability of winning. Different people could come up with a different evaluation of the game state. And thus, we might actually agree on when to double, but if we have a different evaluation of the game state, we might disagree whether or not to double or accept. I was mentioning with somebody, sad situation, imagine someone is getting a divorce. The husband values one house at 500,000 and the other house at 300,000, they own two houses. And the wife values the first house at 300,000 and the second at 500,000. So they both believe there's $800,000 in houses, but they split in terms of which house they think is worth 500,000 and which is worth 300,000. You could actually give each one the house they value more, and both people will feel like they got a better deal. There's a lot more you can say in this problem that I do not want to say with things being recorded. I'm happy to talk about this after the fact. So let's try to imagine now the backgammon problem. So, first to hit, let's say the endpoints wins. And so we know that if you're at K, the probability you get to 1 is just going to, the probability you get to N is just K over N. So let's imagine, here's 0, here's 1, here's 1/2. And let's say this is the doubling threshold P. And we believe that's where we should double. So if we take the limit of what we're doing, what should be the probability we hit 1 before we hit 0? So what's the probability we hit 1 before we hit 0?
For P.
From P. P. Okay, so probability P hit 1 before 0. But now there's another interesting point. Anybody know what the other interesting probability is?
Double acceptance threshold,
What's the double accept?
like the minimum.
Right. So that's going to be something else. But if the probability falls to a certain critical level, we're going to assume the players are identical, that they have the same threshold to double and accept. So what's the key threshold to fall down to? 1 minus P. And at 1 minus P, player 2 will double. Player 1 always doubles. Without loss of generality, we rename our people so that player 1 is the one who doubles first. Once we hit 1 minus P, now all of a sudden, here, this distance is 1 minus p. This distance here is 1 minus p. So by symmetry, if we fall down to 1 minus p, player 2 would double. And we don't have nearly enough colors over here. This is going to be 2p minus 1. And notice, of course, that if p happens to be 1/2, that has length 0. So now, what is the probability that we hit 1 from p before we hit 1 minus p? So what's the probability that we make it from p to 1 before we go from p to 1 minus p? Say that again.
P over 1 minus P.
Why p over 1 minus p? So if you want, think of it this way. We have an interval now. Here's 1 minus p. Here's p. Here's 1. What's the length of this interval? What's the length of it? Is this p? So if we start here, what's the probability we get to 1 before we get to 1 minus p, where we have an interval now of length p? Before, when we had an interval of n points, if we started at k, it was k over n. It was how far am I from the left endpoint divided by the length of the whole thing. So what should the answer be here? 2p minus 1 over p. So this interval over here, this side over here is of length 1 minus p. This part over here is of length 2p minus 1. So this probability would just be 2p minus 1 over p. And similarly, what's the probability I would hit 1 minus p before I hit 1? Then it would be the length of the blue, 1 minus p over p. And if I add those, what do they sum to? They sum to 1, which is reasonable because I either hit 1 or I hit 1 minus p. So this is my model, and this allows me to actually simulate the game much, much faster because I no longer need to toss a coin. I just go, hey, look, if I'm at the 70%, then I've got to get another 30 points to get up to 100, or I have to lose 40 points to get down to 30. And the probability I get those 30 points before I lose the 40 points, I can figure this all out now. Does this seem reasonable so far? These are the key probabilities. And again, I'm just using a continuous analog of what we did before. Okay, so if we're good on this, now let's try to do the flow chart. And so this is where things get a little bit annoying. So we're going to start with the game worth 1 point. And then we're going to see what happens. So start at 1 point. Start with player 1 has probability p of winning and doubles. Okay. Accepted. Now it's worth 2 points. Player 2 has the doubling cube and find the expected value. If player 2 declines, then player one gets what? So if player two declines, how much does player one get? 1 point. Then player one gets 1 point. So X will be the expected value for player one after doubling a game worth 1 point with player two accepting and player one winning P% of the time. Okay. So at this point, the game is actually worth 2 and player 2 has the cube. So game is worth 2 now. Player 2 has the cube. Okay. So let's do my flow chart. So my start, game was worth 1, now doubled and accepted. Player 1 wins P% of the time. So we all agree that this is my start. And my expected value that I'm trying to compute is X. So there's 2 possibilities. What are the 2 possibilities from this point?
Either go to 1 first, or you go to 1 minus.
Good. So we either go to 1 first, or we go to 1 minus P. Right? So here we end, well, I guess we should have 1 going on the right. I think that makes more sense. So end at 1 without going to 1 minus P. Player 1 gets 2 points. And so we're going to have a +2 here. And what's the probability that we get to 1 first? Well, again, we're looking at this, shortened thing. Here's 1, here's P, here is 1 minus P, right? And so the probability that we go from P to 1 was equal to, was it 2P minus 1 over P? And the other one was, I think, P, 1 minus P over P, right? I will double check. 2P minus 1 over P, 1 minus P over P. Okay. Everybody's comfortable with those probabilities? So here, this is going to be, happens 2P minus 1 over P% of the time. Now, if you think about it, P should be more than 1/2, right? So this is at least going to be a positive number. And the closer P is to 1, the closer this is to 100% of the time. Okay. Now, what happens if we end at, so now we reach 1 minus P before we hit 1. Player 2 doubles. Player 1 accepts, has cube. Game is worth 4. And this happens with probability 1 minus P over P. Now, what could happen from this point?
Zero first, or the other.
Good. So we could So here we hit 0. Player 1 loses 4 points. So in terms of the expected value, this would be a -4. So what's the probability? And this is, we hit 0. This is before we hit P, right? Because once we hit P, then player 1 will double. So we'll assume we never hit P, we hit 0, player 1 loses 4 points. What's the probability that happens? So we're at 1 minus P now. So now we need to draw, yet another picture. Let's do some purple. So here we're at 1 minus P, P, and 0. So what's the probability if we start at 1 minus P, we hit 0 before we hit P? That should be this length here is 2P minus 1. This length here is 1 minus P. Notice they add up to P again. And so the probability that I'm going to hit 0 before I hit P is just going to be the length of the side I've already covered, the P to 1 minus P, divided by the length of the whole thing, P. And so I would get that this would happen with probability 2P minus 1 over P. Or I could return to P, player 1 doubles, player 2 accepts, has cube, game is worth 8 points. And this is where I may be making a mistake, and so I really want you to pay attention, as opposed to the rest of the lecture where I want you to be twiddling your thumbs. So what's the probability that I come to here? That's just going to be 1 minus P over P. What is the expected value now that I'm at this situation? So X is the expected value when the game was 1 point, player 1 doubles, player 2 accepts, player 2 has the cube, and the probability of winning was P. Look at how much we have in common. Player 1 has just doubled, player 2 has just accepted, player 2 has the cube. The probability of winning is P. Initially, the game was worth 1 when player 1 made the initial double, which was accepted. Now, how much was the game worth when player 1 doubles? Before it's accepted, how much was the game worth when player 1 doubled? No, at this point over here down the bottom. 4. Player 1 had doubled, it was accepted. Player 2 doubled, it was accepted. So I claim that the expected value here should be 4x. Is it was worth 4 times as much. And so this is the flow chart I get. And so trying to squeeze everything, I would get x is equal to 2p minus 1 over p times 2 from the first part, plus the next one is we lose 4 points. So that's going to be, I guess, a minus. And the probability we get here is 1 minus p over p, 2p minus 1 over p times 4. I'll do it as -4, just to make it all pluses. And then the last one is that we had a 1 minus p over p times 1 minus p over p times 4x. Does everybody agree with that algebra? Going through the 3 paths? The 3 paths we have to worry about is we have, whoops. The three paths we have to worry about is we have this path to 2, we have this path to -4, and we have this path for x. So just to keep the, so coming over here, if I paste this, so what I get is x is equal to 2 times 2p minus 1 over p plus, I'm sorry, minus 4, minus 4, minus 4 times 1 minus p, 2p minus 1 over p squared, plus 4x, 1 minus p squared over p squared. So if I do the algebra properly, I end up getting x equals 2 times 2p minus 1 over p minus 4, 1 minus p, 2p minus 1 over p squared. Bring the 4x, all that over to the other side, and then I'll have x minus that. So then bring that back, and it would become 1 minus 4, 1 minus p squared over p squared. And then let's multiply by p squared over p squared to clear denominators. And if you just do the algebra, oh good, I did remember my glasses so I can actually see it. So when the dust settles, I end up getting 12p squared minus 14p plus 4 over negative 3p squared plus 8p minus 4. So that's what I end up getting. Now, if decline, player 1 gets what? One point. So we have to compare 1 versus 12p squared minus 14p plus 4 over negative 3p squared plus 8p minus 4. So if the expected value of player 1, if this expected value, if this is greater than 1, player 2 should what? Reject, decline. And if it's less than 1, player 2 should accept. And so what's the critical threshold? So 5 seconds left. What's the critical threshold? When equal. And if I timed things well, yes, that gets us to the slide, which was waiting there. And there's my plot, and I'm getting 0.8. So if my analysis is correct, I believe 0.8 is the point where you're indifferent between doubling and not. If you double before 0.8, the other person should accept. If you double after 0.8, they should decline. And this can guarantee getting 1. So this is a good place to stop. I'm sorry that there's not time to hear your comments about this. I would love to hear that. If people are going to be around on Friday and want to just get together, have a coffee and talk about this, just email me, let me know. I'd love to compare this with your analyses. This was the best I was able to get to. And it all depends on, is this a reasonable model?